Okay, so what we discussed about the closed bosonic string revealed the important role of modular invariance that came out as a bonus. It will be really the guiding principle to construct a spectra of closed strings, and combined with a crucial observation of Liozzi, Scherk, and Olive that I will try to explain. So the point is to introduce fermions. It was done in 2 steps, apparently unrelated. The first one was more elegantly motivated by Pierre Ramond. He was looking for a string analog of the Dirac equation. The second one was done in a more roundabout way by Neve and Schwartz, but they ended up to being 2 halves of the different of the same picture. The observation is that you can modify the action of the string, let's say in this Polyakov type form, and you can do this adding fermionic terms to the bosonic ones. The way this is done is transforming the 2-dimensional theory in a 2-dimensional supergravity. But as you will see from the next lecture, you cannot write even a kinetic term for the gauge field of supergravity, which is a gravitino in 2 dimensions. And so the additional terms are a conventional looking Dirac term, let me call this thing gamma A bar, say, d mu, no, dA actually, sine nu, eta mu nu, and here there is something, the Filbine, the inverse Filbine rather, because when you introduce fermions, you cannot work with the metric itself, you have to work with the square root of the metric, the Filbine. Then there is an additional term which contains the gravitino, and contains the gravitino in the following form. I used this kind of indices. There is a B, there is an A, then there is another term here, which involves the psi's, the derivative of x, and another term which involves the gravitino and psi itself. And what happens is that this coupling vanishes because you can fix a gauge in which chi A is gamma A times, actually, yeah, times, this is a bar actually. So gamma A times, say, y. And then in 2 dimensions, gamma A, gamma B, gamma A is 0. So if you want, it's a supersymmetric counterpart of the fact that sigma disappears from here. Lo and behold, the only sign of supergravity is in this coupling of the gravitino to the other terms. And this term disappears. The other terms go in a free form once you do this kind of, perform this kind of step that I told you about, the gauge fixing of the metric. And basically you end up with a theory of free fermions and bosons. So like in the bosonic case, you had a free theory of bosons. In this case, you end up now this is all free. There's no, and the rest vanishes. However, like in the bosonic case, you retain the equation of motion for gravity. Here you retain the equation of motion for the gravitino. And the equation of motion for the gravitino is the condition that this supercurrent sorry, what did I write? I meant dx, not this thing. I wrote something. I said something and I wrote something incoherently. So the gravitino is psi mu dx mu. So this is the supercurrent. And then you have this energy momentum tensor, which is dA x mu dB x nu minus 1/2 eta EB dx squared plus a similar fermionic contribution coming from the kinetic term. This should also be 0. Then you go to the light cone, and then you do the same thing that we did before for bosons. You eliminate all the oscillators in the plus direction, and you put psi plus equals 0. That's the gravitino has disappeared altogether because this term vanished, and then the equation of motion for the gravitino gave us this condition for the supercurrent. Now, the equation for the supercurrent, once you put psi plus equals 0, since this equation is psi plus dA, say, of x minus plus psi minus dx plus psi I dxi equals 0. So this guy is not there. The derivative of x plus is a constant. So this equation determines psi minus in terms of the transverse oscillators. So you start with the psi mu and x mu, but only the transverse part of x mu dxi are left, and only the transverse part of psi are left. The question that remains open is whether the psi's are periodic or antiperiodic. If the psi's are antiperiodic, and therefore do not have a zero mode, then you have something called the Navier-Schwarz sector. And if the psi's are periodic, you have what is called the Ramond sector. And this can be done independently for the left moving modes and the right moving modes. Because the Dirac equation that is written here, if you write it explicitly, maybe I can do that for you. You can use for gamma 0 this quantity, and for gamma 1 this quantity. And so if you write the Dirac equation, gamma 0 d0 plus gamma 1 d1, you see that it becomes d0 plus d1 here, and minus d0 plus d1 here. And so if you look at the two components, psi L and psi R, or this psi because it's two-dimensional spinor, one of them satisfies the condition d0 plus d1 of psi R equals 0, and the other one satisfies d0 minus d1 of psi L equals 0. So this means that psi L is expressed as a sum of modes, say, let me call it psi Ln, or R, let me say psi L R, let's say, and then you have e to the 2I R. This is left moving, so it's a function of tau, it's left moving, so it's a function of tau plus sigma. And the right guy, similarly, has an expansion with modes of the other type. So you see that there is a difference, no, between the bosonic, actually two differences between the bosonic and the fermionic case. The fermions, half of the fermions, so to speak, has only modes on one type, and the other half has the other modes of the other type, whereas the bosonic coordinate has both, no? Has both the left moving and the right moving part. For the sake of comparison, recall that x mu is expanded like this. So you see the first difference is that you have two spinor components. One has one type of modes and one has the other type of modes. They live independently, whereas the bosonic coordinate mixes both of them. There is a second important difference. That is the one that allows the Navier-Schwarz and Ramond sectors. And the difference has to do with the space-time symmetries that you demand by this uncompactified version of the string spectrum. I said it but a bit quickly before when we talked about D equal 26. Out of the bosonic coordinates, you can construct the generators of the Lorentz group. In fact, the whole Poincaré group. So you can construct Noether charges for this two-dimensional theory, which are to be integrated over space, which means over the string, the space coordinate on the string world sheet. And the Noether charges are the zero modes that you build that way. So you will have a momentum, you will have angular momentum generators, but there is an important fact that the contributions of fermions, say to the angular momentum generators, are of this type. And so you see that there is a zero mode, so they are periodic, these contributions, independently of whether psi is periodic or antiperiodic. And this gives you the freedom to choose two different types of boundary conditions for fermions, periodic or antiperiodic. So when you write an action like this, you have these two different choices independently for the left movers and the right movers, to take them periodic or antiperiodic. The big difference is that if they are antiperiodic, then there is a zero mode, and so the fermionic oscillators satisfy equations which are similar to the ones of the bosonic ones. Remember that you only have the transverse ones. Psi plus is 0, psi minus is solved by this condition, you only have psi i's. And then you have this equation here, where this guy is delta Rs, delta Ij. Okay? Now, this is true if R and S are half integer. So 1/2, 3/2, minus 1/2. This is the Navier-Schwarz sector. In the Ramond sector, the index is usually called N. M minus N, I meant here. So the psi m with m positive are distraction operators, the other ones are creation, similarly here. But there is a big difference. And here there is also the psi 0. And the psi 0 are like gamma matrices. So it means that the vacuum of the Ramond sector is not a singlet. It's something where the gamma matrices act correctly. So it's a spinor space. So the Ramond sector describes spinors. Be careful to listen attentively to what I say. The Ramond sector describes spinors on the left and spinors on the right, which means that when you put them together, you can also describe bosons, because spinor times spinor is a boson. That's what people call the Ramond sector. So for closed strings, you have 4 sectors: Navier-Schwarz, Navier-Schwarz. Boson times boson is boson without any question. Ramond, Navier-Schwarz, or Navier-Schwarz, Ramond, they are fermions. And then there is an additional subtler bosonic sector, which is called the Ramond sector. So you have 4 independent sectors. So let's now try to go quickly to the bottom of the story. Understandably, I skipped some steps, but more or less we can fill them up. No? Suppose now we want to compute the partition function of this theory. Well, actually, we should do something before that. We should understand the critical dimension. So let's do it. Let's start from the Navier-Schwarz sector. Navier-Schwarz sector is easier, right? Because in the Navier-Schwarz sector, the vacuum is really a scalar. Okay? So the vacuum is a scalar, and then the lowest excitation of the scalar mode is this guy here. You also have alpha minus 1 I on the vacuum. I'm considering the open. but that's twice as high in mass. So, and this guy must represent the components of a vector. Again, they're only transverse, and so this vector better be massless. So all we need to do in the mass formula, which will be m squared equal 4 over alpha prime times n of the x, so to speak, plus n of the psi minus a shift, we have to understand what this shift is. Now, this shift comes from d minus 2 bosonic coordinates, and then d minus 2 fermionic coordinates, say delta psi. Remember that today I gave you a formula for this delta, and I told you that delta is minus 112, 1 plus 6 alpha times alpha minus 1, which you can verify by computing this geometric sum and throwing away the infinite part. However, there is another subtlety, namely that the psi's are anti-commuting. And you may recall that whereas the bosonic oscillator has this form, which you usually write in the form, say, h bar omega, if you want to keep all these things. You usually write in this form. So the 0-point energy is positive. The fermionic oscillator, let me call it A hat, presents itself in this form. Because the oscillators for bosons satisfy that the anticommutator of A and A dagger is 1, whereas these guys satisfy that the anticommutator is 1, plus the anticommutator with themselves, which is the manifestation of Pauli principle in this case. So now you see that if you rearrange this quantity here in the other way, so this quantity rather in the other way, then, sorry, maybe I should have written it like this to keep the convention properly. So this is like a number operator. And if I rearrange this quantity, then I get plus another A dot dagger A dot, but minus 1/2. So the vacuum energy has an extra minus sign for fermions, which is one of the reasons that people got excited about supersymmetry. And if you want, is what saves the day with supersymmetric strings. Bosonic and fermionic excitations contribute oppositely to the vacuum energy, and therefore supersymmetric strings will not experience any back reaction on the vacuum on the basis of what I told you this morning. For the time being, the important observation is that here we have to use this formula with alpha equals 0, which is minus 112, for the d minus 2 bosonic coordinates, and this formula with alpha equal 1/2, because in the Navier-Schwarz we are shifted the modes by alpha. And if we write alpha equal 1/2, what do you get here? 3 over 6 over 2, you get 3, and here you get 1/2 minus 1. So you get 1 minus 3/2. Altogether is minus 1/2. But this would be the computation for anticommuting bosons. For anticommuting fermions, there is an extra minus sign in front. So in other words, these guys contribute minus 1 over 24. I repeat, there is an extra minus sign in this formula because this is tailored for the boson case. For the fermions, you start with a plus here, because for the reason I told you there. And then, in the Navier-Schwarz sector, alpha is 1/2. And if you put alpha equal 1/2 in that formula, instead of getting this contribution, you get the contribution with an overall minus 1/2 instead here. So minus 1/2 would be plus 124, but since they are fermions, is minus 124. Now add these numbers. This is 1 over 24 plus 2 over 24. Altogether is minus 3 over 24. So together is minus d minus 2 over 8, because 3 over 24 is 8. Now, then, this is the total amount, but there is an error here because the delta is always divided by 2 for the same reason that we had we had not 112, but 1 over 24 in the other case. The reason is that these n's come from two contributions. The well-ordered one, alpha minus n, alpha n, and the badly ordered one, alpha n, alpha minus n. So the n gets a factor of 2 with respect to this reordering. So lo and behold, here you get nx plus n psi minus d minus 2 over 16 times 4 over alpha prime. This is the squared mass for the fermionic string spectrum in the Neve-Schwarz case. And now you see that for this case, nx is equal to 0, but n psi is equal to 1/2. And if you want those vectors to be massless, d minus 2 must be 8 or d equal 10. So let's take this thing for granted, because from the basis of what we said today, that's what it should be. So we work in 10 dimensions. And now let's compute the analog of what we did this morning. We imagine to put the level matching condition. And then instead of computing the trace of Q to the L0 minus 1 times the conjugate, we have to compute this guy with minus 1/2. Because now the shift is minus 1/2. You see it from here. Because if d is equal to 10, this guy is minus 1/2. For the bosonic case, it was minus 1. The difference is that this quantity, sorry, today I called it n, is that n has two contributions. N has a bosonic contribution, and then has a fermionic contribution. The bosonic contribution is what we computed today. I don't need to redo it. It's exactly identical. So what is this bosonic contribution here? Is the product of 1 over 1 minus q to the n, but there's a difference. It's to the 8th power, not to the 24th. Okay? Then I can put another square root of q outside, which is this guy here, and we can concentrate on computing q to the n psi for the fermionic oscillators. I didn't derive completely this formula, but you can guess by analogy with the bosonic case. What is n psi? Is the sum of the, let me use the letter B now, just because it's the sum on R, where R goes from 1/2 to infinity, all half integers, is the contribution of the fermionic oscillators weighted by the corresponding rescaled frequency. Before it was an integer, now it's 1/2, 3/2, 5/2, and so on and so forth. So this is the fermionic analog of what we wrote today, sum on n, say a dagger n, an, which came from alpha minus n, alpha n. In the fermionic case, the oscillators are conventionally normalized, and the frequency factor comes out in front. Okay? Now let's do like today. We pretend to have a single oscillator. We have 8 of them. And so we compute the trace of q to the r, br dagger, br. And then eventually we will raise it to the 8th power because we have 8 oscillators. And again, you know very well what to do here from elementary statistical physics, or if you want, from the fermionic harmonic oscillator. The fermionic harmonic oscillator has only one state, which is the vacuum, and one state, which is the occupied state. And so this stuff is 1 plus q to the r. Before, in the bosonic case, we had to sum over arbitrary occupation numbers, no? Arbitrary excitation numbers of the harmonic oscillator. Here, Pauli's principle stops everything. There's either 0 or 1 quantum. And so the expression that we had in the bosonic case, which was 1 over q product of 1 minus q to the n to the 24th, is replaced by 1 over square root of q product of 1 minus q to the n to the 8, and then we have product of 1 plus q to the n minus 1/2, let me write it like this, to the 8, n from 1 to infinity. So that it's manifest that we have this half integer moding, okay? This is for the Neve-Schwarz sector. So you see, the vacuum starts at minus 1/2, the bosonic oscillators are 8, but it's similar to what we did before. In addition, we have this numerator coming from the contribution of the fermionic oscillators. Now let's go to the Ramond sector. There are two subtleties in the Ramond sector. First of all, that you don't have tachyonic fermions, or if you want, you can see directly from here. The bosonic contributions, in this case, and fermionic ones, add up exactly to 0 in the Ramond sector, because everything is periodic. So you get minus 112 for the bosons, and plus 112 here in the Ramond sector, because the same kind of periodicity, but they are fermions and bosons. So there is an extra minus sign, which is that minus sign on top. So the Ramond sector starts from 0 mass. In addition, the Ramond sector is degenerate. It's degenerate because they have a degeneracy factor, which is 16, by the fact that the vacuum is acted upon by those guys, which are like gamma matrices. So you have 8 objects like that. You can construct 4 creation operators and 4 annihilation operators out of those. Fermionic, you start from the vacuum and you build up 16 states. So the analog of this construction, so this is the Neve-Schwarz sector, the analog of this construction in the Ramond sector would be 1 product of 1 minus q to the n to the 8, product of 1 plus q to the n to the 8, times a factor 16. And the same thing you can do on the right side. Yes? Distinct sectors of a... Exactly, yes. Because here I only treated the left movers, no? So there are in principle 4 sectors like this so far, but you'll see it's more complicated. So you have to imagine to take this guy times the conjugate and all these things. You have 4 contributions. Exactly. And how you put them together will give you the one type of superstring theory or another. The problem is that what I did now is conceptually wrong, which is what Liozzi, Scherk, and Olive first understood. And the reason is the following, that as I told you, let's look at the Neve-Schwarz sector, which is simpler to characterize. The states that I built on the vacuum are this, psi minus 1/2 I vacuum, alpha minus 1 I vacuum. You see what's wrong with these states? Remember that the psi's are anticommuting. And so I'm describing part of the bosonic spectrum in anticommuting terms and part of the bosonic spectrum in commuting terms. Makes no sense, no? It violates spin statistics, if you want. Bosonic modes should be defined in terms of commuting vectors, if you want. And fermionic modes in terms of anticommuting ones. But here I'm building bosons, and part of them are commuting, part of them are anticommuting. So it's not correct. Here, at the same level, I could have built another state so this thing is commuting, this thing is anticommuting, this thing is commuting, and so on and so forth. Or, depends actually, it's commuting times the properties of the vacuum. But certainly they are of different type. And what Liozzi, Scherk, and Olive told us that we have to throw away half of these states. And they found the simplest way to throw away half of these states. In more complicated context, you will be able to retain this state, and this state, but Liozzi, Scherk, and Olive said to retain this and the other ones. And the reason why they did that is because this choice of projection eliminates the tachyon. Okay? Similarly, although it is less straightforward to see, you can eliminate half of the fermionic modes. And the reason is that you can subject the vacuum to a Weil projection. Or to be more precise, the vacuum is a spinor, and the irreducible, the smallest spinor representation that you can have in 10 dimensions is the Majorana-Weil representation. A Majorana spinor is a real spinor. In 4 dimensions, a Majorana spinor, a Weil spinor is a different way of writing the same thing. People sometimes distinguish them because one is has no charge, and therefore you can add also what you call a Majorana mass for that. But from the point of view of the kinetic term, they are completely identical. They can be mapped into one another. In 10 dimensions, the Majorana and the Weil conditions are independent. So you can have an object which is Majorana and Weil at the same time. And in fact, it's true also in 2 dimensions. Because in 2 dimensions, I showed you the distinction between the 2 Weil components, but no one can forbid you to work with self-conjugate Weil components. Those self-conjugate Weil components are, in fact, to be really precise, the psi L and psi R are of our case. And the reason is that you have 2-dimensional supersymmetry, and in order to have 2-dimensional supersymmetry, you need to pair. So what replaces diffeomorphism in 2 dimensions is 2-dimensional supersymmetry that pairs the x coordinates with Majorana-Weil fermions. So in other words, those fermions are self-conjugate, which was sort of implicit in the fact that I told you that B minus R is BR conjugate. I'm trying to tell you too many things at the same time, but to summarize, the fermions psi's are Majorana-Weil in 2 dimensions. The vacuum is a priori a Weil spinor in 10 dimensions, out of which you see only the physical polarizations, of course. And why are the physical polarizations only 16? Because the physical polarizations are determined by subjecting a generic spinor to the Dirac equation. And the Dirac equation is like a projection, halves the number of components. However, no one forbids you to perform an extra projection, which is dividing this 16 by 2. Now, what happens in the massive cases, in massive states, is more complicated. And the reason is the following, that you subject, the vacuum has 2 projections, the left Majorana-Weil and the right Majorana-Weil, okay? So if I said Weil before, I didn't say it correctly. The vacuum a priori is a Majorana spinor because it comes from the psi's. And now we can subject it to the Weil projection. This is the correct ordering, okay? What happens is that this projection here actually flips the chirality between the sectors. So you start from something which is left, and then the excitations with an odd number of these fermionic oscillators becomes right. Left, right, left, right. The only thing is that overall the number of states is solved. Let me say it more clearly. That was not successful. In covariant language, what you are doing on the vacuum you are projecting it by the analog of gamma 5 by minus 1 to the n of these d oscillators, where nd is the sum of n, dn dagger, dn. So you start from the vacuum, so you impose this condition, say, minus this thing equals 0. So the vacuum, you project it with gamma 11. So the vacuum satisfies 1 minus gamma 11 on the vacuum equals 0. But for instance, the states, the n dagger, use a different vacuum such that 1 plus gamma 11 on this thing is equal to 0. So depending on the number of these dn's, sorry, I put an n here, but there's no n. It's just the number of dn's, not the level of mass number. So the Liozzi-Scherk-Canoli projection is precisely this. You have two halves of the Majorana 10-dimensional vacuum, the left and the right. And then you use one or the other according to the number of d oscillators by which you build the states. Altogether, it's half of as many states. Since the counting in the partition function is just counting the states, you have just a factor of a half. But we will shortly become more refined than that. Okay? So, in order to become more refined, we have to understand a little bit of the mathematics that lies behind all this. And the mathematics that lies behind all this has to do with theta functions. Now, theta functions are Gaussian sums. And the theta functions of interest for us are what I call the 4 theta constants. These sometimes are called the even characteristics. And this is called the odd one. Moreover, this quantity is identically 0. Now, these theta functions have another representation. You know that, for instance, the sine function, sine of z, has two different representations. The first one is the familiar one. Is a power series, and the other one is an infinite product that exhibits the zeros. The same thing is true for the theta functions. They have two different representations. One is as sums and one as products. And in particular, they are like this. Theta 0, 0 of 0 and tau is the product of 1 minus q to the n, 1 plus q to the n minus 1/2 squared. Theta 0, 1/2 theta 1/2 0 is 2 times q to the 1/8 product of 1 minus q to the n, 1 plus q to the n squared. Now, theta 1/2 1/2, if you were to compute it with a non-zero entry z, it would be non-zero. It just vanishes at the origin. Okay? However, these theta functions have well-defined transformations under tau goes to tau plus 1 and tau goes to minus 1 over tau. Tau over tau plus 1 is easy to see because is just q becomes e to the I pi q. Sorry, e to the 2 pi I q. So q to the n remains q to the n, but q to the n minus 1/2 changes sign. So this means that theta 0, 0, let me just write this, not the argument, becomes theta 0, 1/2, and theta 0, 1/2 becomes theta 0, 0. Theta 1/2, 0 picks a face. Theta 1/2, 0 picks a face, because the only thing that you get an e to the I pi over 4 here. Theta 1/2, 1/2, if you were to compute it for z different from 0, it would pick exactly the same face. Now, it's a bit formal to say that 0 becomes a face times 0, because, but it's very important, because this is what is called the resolution of the ambiguity. Remember that I told you that this Liozzi-Scherken-Olive observation halves the number of states in the Ramond sector. Halving the number of states in the Ramond sector can be done in a way that distinguishes whether the state is left projected or right projected. And in order to do this, we have somehow to retain this quantity, because all we need is the modular transformations of this quantity. So we can split the spectrum into 4 parts. First of all, let me see what the spectrum is like. Let's write the spectrum in terms of this notation. We have it there. We have at least the naive beginning of writing this spectrum in terms of there. Now you'll see that if you follow this step, then the rest becomes very algorithmic. Consider the first expression there. And I want to write it in terms of theta 0, 0, the one on top here. This one. If I want to write in terms of theta 0, 0, I must multiply by 1 minus q to the n to the 4th and make this 8 at 12. And now you recognize, if you look by comparison at that stuff, that this Neves-Schwarz contribution, at least if you want this naive Neves-Schwarz contribution, is theta 0, 0 of 0 and tau to the 4th power divided by eta to the 12. Now, since you know that an eta to the 8 is the contribution of bosons, then you see that the fermions contribute this quantity. Not 8, but 4. I made a mistake here. So this means that every pair of fermions contributes just by reading this formula. Since I have 4 pairs of fermions, 8 altogether, then I get that formula to the 4th. Okay? In the Ramond sector, similarly, you can write the contribution as the 4th power of theta 1/2, 0 divided by the 12th power of eta. Split again the bosonic part, which has no subtlety with plus and minus periodicity. And then you get theta 1/2, 0, 0 tau, eta to the 4th. So it means that in the Neves-Schwarz, they contribute this amount. In the Ramond, they contribute theta 1/2, 0, 0 tau divided by eta. How do we implement the Liozzi-Scherken-Olive prescription? We have to separate the even numbers of fermionic oscillators from the odd numbers of them, because they have opposite statistics. They don't live well together. And this can be done considering the following 2 combinations. The first one, I will call it O8. And the second one, I will call it V8. So far it's just a name, but look at it. Look what happens in that combination. Let's see inside what is there. What's in there, it's up to a factor of q to the 4 over 24 and a factor of half. Inside I have the following contribution: 1 plus q to the n minus 1/2 to the 4th plus the product of 1 minus q to the n minus 1/2 to the 4th. So this function, this combination, keeps only terms even under q goes to minus q. Actually, under q to the 1/2, interchange with minus q to the 1/2. Because if I look at this expression, this is sent by itself by sending q to the 1/2 into minus q to the 1/2. Because it's only the overall sign. So the q to the 1/2 makes it flip, and q to the n does nothing. But what is q to the 1/2 in this formula? I don't know. Maybe I should have gone more slowly with the other partition function. Let's back up a little bit. Let's try to read the partition function. Let's go back to the bosonic case. What is the meaning when you have this partition function like this? Sorry? Let's make the break, yes. So that I also wash my hands. So during the break, one of you asked, what is the point of rewriting everything in terms of theta functions? And the answer is that writing in terms of theta functions, this expression gives us immediately the behavior of these expressions under modular transformations. You could say that mathematicians did the work for us, but in fact the work in this way of formulating things is relatively simple. It only rests on an important trick which is called Poisson summation. And lo and behold, writing the contribution in terms of theta function tells us how they transform under modular transformation and helps us to build modular invariant combinations. Now, what I wanted to show you, I was doing it at the end of the previous lecture, is that the partition function tells you the spectrum very clearly if you learn how to read it. Consider this bosonic contribution to the open string. And let's look at the low-lying states, the same states that we identify directly from the oscillators. We look at them in powers of q. The exponent of the power of q tells you the mass of the state. So the lowest term in this expansion is 1 over q. The coefficient 1 tells you there is one tachyon. And the normalization tells you that the mass is such that alpha prime m squared is minus 1, like the power of q. The next expansion only comes from this term. And so you get 1 plus 24q if you expand to first order. And then you see that you get 24. And the 24 that you get from the expansion of this term is exactly counting the states alpha minus 1 I on the vacuum, the polarization of the vector that sits at that level. Now, if you compute the next contribution, then you will get a term in the expansion of this guy, which is 24 times 25 over 2, q squared. And then you will get 1 plus 24 q squared that comes from the second term. Now you can also recall that this comes from the alpha minus 1 oscillators. So this term is the contribution of alpha minus 1i, alpha minus 1j. And this term is the contribution of alpha minus 2i. If you count correctly, like we did in the second round this morning, you find the polarizations of a massive spin 2, and so on. So you can recognize the whole spectrum with the same difficulty that we had in terms of the oscillators, of course, but in a very compact way. These are generating functions of the spectrum. Now, better objects are this O and V, because these guys count the terms that are even or odd under q to the 1/2 goes to q minus q to the 1/2. So for instance, this one will start with a tachyon, but it will go to the massive spin 2 level. This will start with a vector, and then it will go 1 unit up in mass level. And that's why they are called O8 and V8, because this starts with the O, which is like a scalar, and this starts with a vector. The low-lying state is manifest. It's a scalar here, it's a vector here. There are two more combinations like this. And these combinations are called S8 and C8. And C8 is the same thing with a minus sign. Naively, you would say that these two terms are numerically the same, because S8 is 0 like the trace of gamma 5 is 0 in 4 dimensions. But having one or the other separates the states into two different sets that correspond to the opposite projection of the vacuum. So it's a common trick in conformal field theory to resolve the ambiguity and treat these guys as different ones. Although numerically they are the same, you treat them as different ones and you get a finer touch on the spectrum. Because you also take into account, considering, regarding them as different, the difference in the projection of the vacuum and of the excited states. Why can you do this thing in a useful way? Is because you can get a definite modular transformation, as I said, for theta 1/2 of 0 and tau, computing it for z less, computing the transformation of theta 1/2 of z and tau for z small, and looking at the fact that the limiting form of these modular transformations is well defined even when z goes to 0. So at that point, you prove by the properties of the modular transformations of the theta functions that under tau goes to 1 minus 1 over tau, usually it's called the S transformation. These guys transform in a very simple way. So if you read the explicit, it means that O8 goes into half of the sum of O8 plus V8 plus S8 plus C8. V8 goes into 1/2 of the sum, do the matrix multiplication, O8 plus V8 minus S8 minus C8, and so on. Okay? And now, and each of them transforms with a definite phase under the transformation tau goes to tau plus 1. This is usually called the T transformation. And this you can see directly from the definition, because theta 0, 0 is mapped into theta 0, 1/2, and vice versa, and eta to the 4 gets a phase, because there is a q to the 4 over 24, which is q to the 1/6, and this gets a phase, which is e to the 2 pi I over 6, right? And which means e to the I pi over 3. So in other words, this guy here, it's diagonal, this gets e to the minus I pi over 3. V8 has a different phase because O and these two guys are interchanged, so there is a minus sign. Eta to the 4th is the same. Remember that theta to the fourth has a prefactor which is q to the 1/4. Sorry, to the 4 over 24, like I said previously. This is q to the 1/6. And then under the modular transformation, tau goes to plus 1, q picks this factor. That's why I put this guy here. For V8, you get minus e to the minus pi over 3. And for these guys, you get a factor here. So these guys transforms into themselves, but there is a factor, because remember that q to the 1, theta to the 4 becomes gets q to the 1/2 on top. The reason is that I told you that theta 1/2 0. Sorry, here I'm talking about this now. O8 and V8 we did. I'm talking about this. Theta 1/2 0 contain a q to the 1/8. Raised to the 4th power is q to the 1/2. Q to the 1/2 gets a factor e to the 2 pi I over 2, which means e to the I pi. This eta to the 4th, I told you, it's e to the minus I pi over 3. So this T matrix is notice that the first, this is the diagonal matrix and the last three entries are identical. This should be like that because SO8, which is the transverse Lorentz group, has a triality. The three representations are somehow equivalent. Now, once we know all this, these S and T matrices, we can do the whole story. Because we know that the partition function on any model that we build out of these 4 entries, let me call them characters. So let me call chi the set of O8, V8, S8, and C8. The generic partition function will be the sum on I and j, certain coefficient, let me call it nij, chi, chi bar j, chi bar I, chi j, say. Or chi I, chi bar j, say. So they are numbers, I mean, somehow it doesn't matter. And the whole point of building the possible superstring theories in 10 dimensions is to choose this matrix. This matrix here is a matrix of integers, because you must have integer number, so states. And then Bose and Fermi have to enter with minus signs, relative minus signs. So a better way to do this is to work with the different bases of characters. Instead of working with O8, V8, S8, and C8, we work with O8, V8, minus S8, and minus C8. The T matrix remains the same because it's diagonal. The S matrix changes because if I work with this basis of characters, I'm automatically putting the minus sign for fermions. Now what happens here is that the first line becomes minus 1, minus 1. All the Fermi terms disappear, change, no? So this guy becomes 1, 1. And the reason is that the coefficient in this form of, where did I have the other one? I lost it now. How come it disappeared? Maybe it was there. Oh no, here it is. You see, just the entries that multiplies S8 and C8 are flipped in sign because I'm flipping them the sign inside. And the line also is flipped because S8 and C8 are. So in other words, the thing, it becomes like this. This is minus 1, this is 1. And then S into S now doesn't change, in fact, because it's minus S to minus S. So this thing becomes this. And now the question is, what kind of sesquilinear combinations can I build out of this 4 characters? Now, working with that basis, this is a matrix of integers which are greater than or equal to 0 in the other basis. And the second condition is encoded by that. Why a matrix of integers? Because you cannot have half of a state. The states are representations of the Lorentz group. You cannot have half of a vector. You must have a full vector. So let me show you what the solutions of this story are. There are only 4 solutions. The first solution is V8 minus S8, absolute value squared. The second is V8 minus S8, V8 bar minus C8 bar. The third one is O8 absolute value squared plus V8 absolute value squared. And the fourth one is this. This theory is called 2B. This theory is called 2A. This theory by analogy is called 0A. This theory by analogy is called 0B. Because this is completely diagonal, completely absolute value squared, and this is sort of flipped in the Ramond sector. These theories here have only bosons, which answers to what some of you asked before. And the reason is that this, if you want, is a Neves-Schwarz, but these are Ramond-Ramond. Ramond-Ramond are other bosons. This is different. Because this theory, if I expand it, becomes V8 V8 bar minus V8 S8 bar minus S8 V8 bar plus S8 S8 bar. And this notation has another big advantage, that the low-lying states are manifest. So we can read them independently of the fact that these V's, O's, S, and C describe an infinite number of states. We know that this infinite number of states starts with a scalar, a vector, a left spinor, a right spinor. So the low-lying states are manifest here. What states would I get here? A bivector with no symmetry. What is a bivector with no symmetry? It's a symmetric traceless part, an antisymmetric part, and a trace. So this sector here describes the polarization coming from a metric, an antisymmetric tensor, and a dilaton. What happens here? I get a state which is a vector spinor. But here I'm talking about in terms of physical polarizations. A vector spinor is not an irreducible representation, like a symmetric tensor is not irreducible because you can take out the trace. If I have a vector spinor, an object of this type, then I can multiply by gamma I, alpha, beta, and get a spinor. You see, I've contracted the vector index. So it means that those states are not irreducible. This state corresponds to the polarizations of a gravitino, which is left, and the spinor lambda, which is right. Why right? Because it's the gamma trace of the previous one, and taking the gamma trace flips the chirality. This state is completely equivalent from the space-time point of view. This is another gravitino left, another spinor right. So I've built a spectrum which contains G mu nu, B mu nu, phi, a gravitino, another gravitino, 2 spinors. How about here? That guy is a little bit more complicated to understand because we have to decompose the bispinor in terms of gamma matrices. And the rule is the following, that 8 spinor times 8 spinor, which is this case, and 8 spinor times 8 spinor conjugate, which is the other case, decompose respectively in the polarizations of another scalar here, another 2 form, and a self-dual 4 form. So a 4 form such that the field strength F mu nu rho sigma satisfies the condition that it's self-dual. sorry, mu rho sigma tau. It's one of these chiral bosons that I told you that they exist in 6 and 10 dimensions. In this case, this guy gives you a vector and a tree form. So the polarizations of a vector and a tree form. How do you see that? The idea is to look at the invariants that you can find in SO8, which will give you the polarizations of the states, and then to recognize what covariant fields upon gauge fixing would give you those polarizations. For instance, the spinor is real, and therefore there is an invariant tensor which is, say, delta alpha beta. That gives you the scalar. The vector, on the other hand, has one index of one type and one index of another type. Let me call it alpha alpha dot. It's like in 4 dimensions, so it appears there. The two form, it's something like this, gamma mu nu, it's a product of this and the conjugate one. So it has two indices of the same type. Anything with 3 indices flips again, and anything with 4 flips again. So that's why they split in these two parts. This is the spectrum, the massless spectrum here is the massless spectrum of 2B supergravity. This is a massless spectrum of 2A supergravity. And these are two purely bosonic theories which have a pathology. Can you tell me what pathology they have? Yeah, but the scalar is a tachyon. So these theories contain a tachyon. So they have the same kind of instability that the bosonic string has. Okay? But you will see that they are good starting points to build something which doesn't have a tachyon. And these are the only 4 solutions of this type. Now, these solutions can be mapped into one another by an operation, which is an orbifold projection. It's important to show it to you at this stage because it anticipates discussion of other facts, and it shows you many other things. Consider that I'm only looking at the integrand of the partition function. The partition function is integral d2 tau over tau 2 squared. Then there is 1 over tau 2 to the 4th eta bar to the 8th. And then there is this quantity here that I'm considering. The rest is modular invariant without any subtlety, so I'm just elaborating on this quantity. Okay? Now suppose that I start from the type 2B theory, so I only concentrate on this quantity, which is V8 minus S8 absolute value squared. And notice that there is an interesting point. This quantity is symmetric under left-right interchange in 2 dimensions, because it's an absolute value squared. Left-right interchange means swapping the holomorphic and the anti-holomorphic part. They are identical because it's an absolute value squared. And on the other hand, it's chiral in space-time because the gravitini have the same chirality and also the spinors. Plus, there is also this self-dual form, which is chiral also. So if you do a parity in space-time, this becomes right, this becomes left, right, left, and this becomes anti-self-dual. So it's a chiral theory, but in 2 dimensions, it has the opposite property, so to speak. It is symmetric under left-right interchange. This will be important later on. Now, let me tell you the following. Take this thing. To be complete, I should take the whole partition function, but I'm elaborating only on this. The rest is completely fixed. And now, take these states and subject them to the following projection, where FL, or FR rather, let me use FR for a reason that you will see shortly, is the right fermion number, space-time fermion number. So I want to take this partition function and try to retain the states which have are even under this projection. Okay? How do I do that? Well, the 1/2 is easy. Applying 1/2 to the partition function is very easy. Just 1/2. If I apply the operator -1 to the FR, then I must change sign to all the fermionic states. So the second contribution here is 1/2 of V8 minus S8 times V8 bar plus S8 bar. Maybe I should have showed you something. I didn't show you something before. Because we can verify that this thing is modular invariant. I gave it for granted, but it's very simple to verify that it's modular invariant. If you take that expression, you can see that V8 goes into that sum, and minus S8 goes into the other sum. So V8 minus S8 goes into itself. So this is modular invariant because V8 minus S8 goes into itself. The tau goes to tau plus 1 gives you phases, but it's an absolute value squared, so the phases are irrelevant. Here, V8 minus S8 goes into itself, V8 bar minus C8 bar goes into itself. So tau goes to -1 over tau is okay. And the phases are equivalent for left and right, but the right is the complex conjugate. So the phases are opposite, and so it's invariant. And this one, to understand how it works, it's better to write O8 absolute value. I mean, either you do the computation, or to do it better, you do 1/2 O8 plus V8 absolute value squared plus 1/2 O8 minus V8 absolute value squared, and similarly for the other one. And then you show that under under T is obvious because they're absolute value squares, so nothing happens. But under S, this O8 plus V8 goes into itself. O8 minus V8 goes into S8 plus C8. But then you do the same thing for the S8 absolute value squared and C8 absolute value squared. You write it as S plus C plus S minus C. Then S plus C goes into O minus V, and S minus C goes into itself. So these are all modular invariant, these four things. It's simple to verify with that matrix. However, if I try to do this projection, this term violates modular invariance, clearly. Because from what I told you, under T is okay, but under S, this term goes into 1/2 V8 minus S8, and this guy goes into O8 minus C8. So I cannot simply project this thing. I must add more stuff. And this stuff is also not invariant under T goes to under T. And the reason is that O, it would be invariant if I had V, not O here. But between V and O, there is 1/2 unit of mass. So if I do an S transformation, I get here. If I do a T transformation, here I get V8 minus S8 minus O8 minus C8. So how do I make it modular invariant? Basically, adding these two more terms, because this is the S transform of this, and this is the T transform of that, and then if you continue to do it, you go back to the same place. The sum of these four terms is modular invariant. The original one was, if I break it, if I project, I break modular invariance, the S transformation, this is T invariant, but under S it goes into this quantity. This quantity is fixed under, so under S it goes back to that. Under T creates another term. And under T this guy goes back to that expression. And under S, O plus C becomes, O plus C becomes what? O plus C becomes, let's see, O plus C. It's invariant under S. So this is invariant under S, and under T it goes back like that. So in other words, if you take this quantity, you try to project, but you add these other two terms, you recover a result which is modular invariant. Let's read more closely what this result is. Well, if you add these two guys, O cancels and C doubles. So you get V8 minus S8 times minus C8 bar. And if you add these two guys, the S8 cancels, and then you get V8 minus S8 times V8 bar. So if you add everything together, basically, you have replaced this partition function. So in other words, by this operation here, you connected these two theories. Similarly, you could connect these two theories, but I can also connect those theories, that theory to the other one. This operation is called an orbifold projection. It has geometric meaning in certain cases. In this case, it's just an algebraic operation. You take, throw away some states, reinstate modular invariance, you need more states. And for instance, if I want to connect this one and the other one, then I have to do a projection simultaneously on left and right fermion number. So this means that V8 minus S8 should become 1/2 of V8 minus S8 absolute value squared plus 1/2 of V8 plus S8 absolute value squared, because here now I flip the fermions from the left and from the right. Now I do an S transformation, and this thing becomes 1/2 of O8 minus C8 absolute value squared. Then I do a T transformation, and this becomes O8 plus C8 absolute value squared. If you sum the first two, then you get simply V8 absolute value squared plus S8 absolute value squared. And if you sum the other two, you get O8 absolute value squared plus C8 absolute value squared. So in other words, by this operation, I can connect all of these theories. Because I can also do a right fermion number thing and connect all of them. They are all connected by these orbifold operations. This is not the connection that people usually talk about. Okay? Now how much time do we have? 15 minutes. Now, what happens is that in the mid-80s, Green and Schwartz computed gauge and gravitational anomalies in 10-dimensional string theories. At that time, the targets were the first two here. They found that the second one obviously was anomaly free because it's not a chiral theory, and a non-chiral theory is automatically anomaly free. The big surprise, actually this was done before by them, by Alvarez, Gomez, and Witten. The big surprise is that this theory here, which is chiral, is also anomaly free. It doesn't have gauge anomalies because it has no gauge vectors, but it has gravitational anomalies. So the energy momentum tensor conservation can be violated by quantum corrections. And there are contributions to gravitational anomalies, from Gravitini, spinors, and also from this guy, which is a chiral object. And what the Alvarez, Gomez, and Witten found, to their surprise, is that the result is 0. Now, I also told you that this theory and this other theory, which, by the way, I should have, I sort of said it, but this other theory has fermions which are non-chiral. So there is a gravitino left and a lambda right. And there is also a gravitino right and a lambda left, due to the different chirality of the Ramond sectors. This theory is automatically anomaly free, but actually these supergravity theories admit a truncation. These are usually, the low energy theories here are usually called 2-0 supergravity or type 2b supergravity. This is called 1-1 supergravity. And there is also another supergravity theory, it's called 1-0 supergravity. This theory has a spectrum which is essentially obtained halving the spectrum of fermions present here, symmetrizing here. So in other words, the G mu nu, B mu nu phi becomes simply G mu nu and phi. The B mu nu disappears. These objects here, they are two copies. They remain in one copy. And then this sector here is projected in such a way that this state and this state disappears. So there is a graviton, dilaton, left gravitino, right spinor, and the two form. Now, if you compute the gravitational anomalies, this theory is anomalous. It's a sick theory. But this is not the only multiplet of states present in 10 dimensions. There is another multiplet of states, which is the supersymmetric Young-Mills multiplet, in which you have bosons, vectors, if you want, and left spinors valued in the adjoint of a gauge group. And what they found, what Green and Schwartz found, is that naively, independently, what Young-Mills multiplet you put into the game, the theory is anomalous. But then they discovered something very interesting, that if you compute the anomaly directly in string theory, you find zero. So there was a contradiction between field theory and string theory, and the reason is that part of the anomaly is cancelled by local counter terms. So an anomaly is really a violation of a symmetry which cannot be eliminated by a local counter term. The local counter term is automatically included in string theory, and in knowledge of supergravity you can include it because it's a coupling which is allowed. And the resulting mechanism is called the Green-Schwartz anomaly cancellation mechanism. However, it doesn't work for any gauge group, but there is a crucial constraint coming from gravitational anomalies that the gauge group should have 496 generators. And there are other constraints that come that involve the matrices, like the T matrices that we heard about today. And now what Green and Schwartz did originally, they showed that this cancellation holds for the gauge group SO32. But the large effective field theory allowed more, and it actually was pointed out right away that there could be other solutions. And the other solution is E8 cross E8. In fact, there is also another solution, which is U1 to the 496 and other cases like that, but they cannot be realized in string theory. And so we knew at that time, for the argument I gave you last time, that an exceptional group cannot be realized with open strings. And on the other hand, this kind of combination was the combination that was known in the only theory of open strings known at the time, was the type 1 superstring theory. And if you want, roughly speaking, the limitations that we found arose from the fact that the open strings carries the charges at the ends. And so what people found, this was done by Gross, Harvey, Martinek, and Rom at the time, that there is another way of constructing string theories, which is a hybrid between the bosonic and the superstring. So if you want, it's superstring left times bosonic right. Strange, right? Because, but remember that when you look at the partition function, it effectively factorizes into a left and a right part. So if you manage to enforce modular invariance and spin statistics, opposite sign for bosons and fermions, then it's okay. But it's only a puzzle. The puzzle is that the bosonic theory here lives in 26 dimensions, so there is an imbalance of 16. The fermionic theory lives in 10. The bosonic theory has another 16 dimensions, where the boson is purely chiral. We already discussed with some of you today that there are chiral bosons in 2 dimensions. And the way to build, to allow chiral boson is essentially to work with a compactification on a torus. And what happens is that these 16 dimensions are compactified on a specific lattice, which has to do with these 2 gauge groups there. One is the lattice of E8 cross E8. Lattice means essentially the lattice of the weights of that. So it means that the momenta are quantized there, and there that gives you the, if you want, the analog torus, if you want to understand it in those terms, but only the right movers. So it's better to think in terms of lattice. And the other one is the lattice of spin 32 over Z2. So if you want, there are 4 classes of representations in spin 32, which are O32, V32, S32, and C32, and this lattice uses only half of them. At the end of the day, what happens is that you have 2 more supersymmetric partition functions, which are modular invariant, but they have different ingredients, so they cannot be compared with the other ones. I write them like this in the spirit of resolving ambiguities. And of course, this thing has to be folded in both cases with 1 over tau 2 to the 4th, eta bar to the 8th. This is what people sometimes now call the HO theory, and this is what people sometimes call now the HE theory. Now, these are modular invariant because the properties of the orthogonal groups are periodic modulo 8. So the S matrix is the same. And so O32 plus S32 is invariant under S transformation like O8 plus S8, exactly, because it's modulo 8. V8 minus S8 is invariant. And similarly, O16 plus S16, and the faces under T transformation readjust. Those are 2 modular invariant combinations. What are the low-lying states here? So let me conclude this lecture in the last 5 minutes showing what the low-lying states of these theories are. If we are good, we should find the low-lying states of 1,0 supergravity plus the low-lying states of Yang-Mills theory. Now, here we are facing the following problem. Now, here I skipped an important detail. Maybe I can tell you that this funny compactification with bosons which have only right moving modes is equivalent to a fermionic, the addition of other fermionic Neves-Schwarz-Ramond type modes here. The reason is that in 2 dimensions, you cannot really perform rotations, no? Because you have time and space. So you cannot distinguish a boson from a fermion rotating around it, right? So there is an equivalence between bosons and fermions in 2 dimensions. And so this particular compactification is equivalent to a compactification with 32 extra fermions. Chiamiamoli, let's call them psi I with an internal index. Maybe psi I bar because they are on the right, or tilde, you want to call it. And so we can look at this at the spectrum and try to see how do this partition function, which are modular invariant, how are the low-lying states done. Now, in this case, you have a left-moving vacuum, which is coming from the superstring, and so it starts at -1/2, and the right-moving vacuum, which starts at -1. Remember that you have to satisfy always level matching. So what runs in the partition function are also off-shell states, but the physical states satisfy level matching. How can you satisfy level matching? Well, for instance, taking psi -1I from the left and alpha minus 1 tilde j from the right, because here you raised everything to 0. Can you have tachyons? No, because the tachyonic modes are different. So they don't satisfy level matching. So everything starts when level matching is possible, the massless level. What are these states? Forget about the fact that one comes from a psi and alpha. This is a 2 tensor with generic symmetry. So it must correspond again to the modes of a G mu nu, a B mu nu, and a phi. If you take symmetric part traceless, antisymmetric part, and trace. You recognize that this is sort of a universal sector. Every string theory contains this sector. Phi will be essentially the coupling constant of string theory, the exponential phi rather. The B mu nu has to do with the fact that the theory is a theory of strings. And the other one is gravity, inevitable. In all these cases, it's impossible to eliminate gravity. There's no projection that throws away gravity and is consistent. And so we found this sector here. Now, the other thing we should find is again the other. So we found this part, no? The bosons of this. Now we should find the other guys. And so the other guys must come from the Ramond sector on the right. So I must have the vacuum of the Ramond sector, and then on the right, and then on the left, I must still put psi minus 1/2 I for level matching, because the Ramond vacuum starts here at 0. And in order to get level matching, you must add an oscillator to the left. What is this? It's a spinor vector, and then I decompose taking the gamma trace out. So this thing, if you want, has a spinor index in it. And so this is the gravitino left and the spinor right. So the first part we understood. Now the gauge part. The gauge part, it means that we have to use these guys. So we don't use the alpha minus 1 or the space-time spinor. We will use the space-time spinor short. But let's start from the bosons. We don't use the alpha minus 1. And we have to use the states of this O32 plus S32. Now what happens is that this guy here starts at level -1. It's like a tachyon. But the level -1 is irrelevant because it doesn't satisfy level matching. So in order to have a chance of satisfying level matching, I must apply psi minus 1/2 I. So I bring this left sector to the vacuum. And then I must apply 2 alpha oscillators. This sector, remember, contains even number of oscillators. Even number of oscillators, let me call it psi I oscillators. So this guy, there will be a psi minus 1/2 bar I, psi minus 1/2 bar J. You see that these are anti-commuting, so this is naturally anti-symmetrized. And this is applied on the vacuum of the Navier-Schwarz sector. So what is this thing? It's like states which are AI, IJ. But these are the physical polarization of NA mu IJ. See, it's antisymmetric. It's an adjoint of an orthogonal group. And then you ask yourself, how about this S32? But remember that the Ramond sector had this famous Q to the 1/8 in front. So Q to the 1/8 for 8 fermions became Q to the 1/2. And so 8 fermions, so S8 contains the Q to the 1/2. S32 contains a Q squared, because so it means that this sector does start at -1, but then the S sector breaks it up by 2. -1 plus 2 is +1, so this concerns the massive spectrum. The massless spectrum is precisely as we said. How about the fermions, the gauge fermions? Instead of putting psi minus y I on the vacuum, we put the Ramond vacuum. And the states are still valued in the antisymmetric of SO32, so you get spinors valued in the antisymmetric of SO32, which is the adjoint. How about this other theory? Well, what changes is only the matter part, no? Because it has different quantum numbers. Now you see that if you want to go and bring this sector to zero mass for level matching, then you must take either two oscillators here or two oscillators here, because this sector doesn't contain odd number of oscillators because it's a no sector. So if you have either psi minus 1 I, 1/2, say I, psi bar minus 1/2 J, or psi minus 1/2 bar I prime, psi minus 1/2 bar J prime, where Ij tells you that you take them from this, and I prime, J prime, you take them from this sector. So you see that you get something which is valid in the adjoint of SO16 cross SO16. But here it's different, because what I told you here, if SO32, if S32 brings you up by 2, S16 brings you up by 1. So you can have other massive, other massless modes if you use a spinor here or a spinor here. So instead of having only the states which are in the, say, I, J, I prime, J prime, you also have something, let me call it capital alpha, or in capital alpha prime. So the states are an adjoint multiplet of SO16 plus another 128 states, which have to do with the spinor. And now 120 plus 128 makes 248, which are exactly the joint representation of any 8 factor. So you have the 8 cross 8 group. Now, of course, to be sure that the group is E8, it's not enough to count the number of generators, no? But you have to look at exactly the quantum numbers, but there is a decomposition of E8 into SO16 such that the adjoint of E8 decomposes into the adjoint of SO16 plus a spinor. So these are the two heterotic strings in 10 dimensions. And now, next time, I will show you that actually, because I don't have time to do it now, that from these heterotic theories, it's possible to build another heterotic theory, others, which are tachyonic, but in particular, it's possible to build another heterotic theory which is non-tachyonic and non-supersymmetric. It's a unique one. The technique is exactly what I used before to go from type 2B to type 2A. So it's an orbifold projection. I can even tell you what the orbifold projection is. Maybe then you can play with it and try to see if you get it. So you start with this theory. And then the projection is the following. You don't touch the left part. And you project the right part. Oh, incidentally, I forgot to tell you something very important. I conclude the lecture with this. Jacobi, when he studied all these doubly periodic functions, found an identity between thetas. And the identity that he found was this. And he called it the abstruse identity, because he didn't know what it meant. In fact, he had discovered supersymmetry. Because if you look at this quantity, this is just V8, and this quantity, you can write it as S8 or C8. So this quantity is essentially that V8 minus S8 is 0, or V8 minus C8 is 0, which also tells you that the partition functions, the first two that you have on top, do not back react on the vacuum, because the numerical meaning of the partition function is proportional to the cosmological constant that you induce by back reaction. And supersymmetry doesn't let them do that. So Jacobi had discovered this identity that written in these terms means that the number of states in the V sector is equal to the ones in the S sector is equal to the ones in the C sector.